Okay, so this is the prep video for section 3.6 on related rates. So let's go ahead and get started. Related rates is based on the calculus part. These are word problems, word problem applications. I know you guys love word problems. Life is a word problem. So these are actually going to be interesting questions that you might want to know the answer to. For example, you know that oil is spilling out of a tanker at a certain rate. How fast is it spreading? That's an interesting question. We can answer that. Or you might want to know, if my production is increasing at 500 units per week, how fast is my profit increasing? You want to know that too. Another good example would be you're pulling a boat in to shore, and it's on a pulley that's coming in at a fixed rate. How quickly is the boat approaching the dock? So these are questions that are actually kind of interesting that we can answer using related rates. And so the piece that we're going to need from calculus is implicit differentiation. And really the part of that that's important is the part that connects to chain rule. So let's write both of those up here. So remember, if I do the derivative with respect to time of t squared, the variables match. That's just a straight derivative, 2t, no problem. But what if I want to take the derivative with respect to time of x squared? Well, now I have that chain rule composite function thing going on. I've got an outside function and an inside function. So I still get the pattern, x squared goes to 2x, but now I have to multiply by the derivative of x with respect to t. So times dx dt. And I purposefully introduced t as our with respect to variable because related rates are about with respect to time. That's the point. All right, so I think what I'll do is I'll do an example and then kind of lay out the steps as I'm doing the example. Otherwise, I'm not sure the steps will make sense just yet. So here's our example. Find the rate of change of volume of a cube if the side length is increasing, actually let me say is changing at -2 inches per second when the side length is 4 inches. Okay. Kind of a basic question, maybe not so interesting, but we're trying to start with something basic. So two things we're going to need to do is sort of pick apart what the words mean, but I'm going to quickly translate those. We'll spend much more time in class. What I want to do is quickly translate this into math and then work through the math process. So find the rate of change of volume. Let's call V volume with respect to time. That's sort of implied. So we're trying to find this. So the first thing I'm going to say is, well, I'm trying to find this rate of change. Do I know any other rates of change? The side length is changing at. That's a rate of change. So the first thing we're going to do as we're reading a problem is to try and determine if, in fact, this is a related rate problem. So that's our first step. Identify the problem is related rates. And how do we know that? We know that because we're trying to find a rate and we know a rate. So that makes it a related rate problem. And then the next thing you want to do is write down what you're trying to find. That's always a good place to start because it helps drive your solution, what you're going to write down, what you're going to look for. So we want to find, let's do it this way. We want to write down the rate to be found. And I like to actually use the word find. So I'm trying to find this. So the next thing is, okay, well, what do I know? So let's start thinking about what we know. So that's going to be our third step. We're going to write down known rates, known values, known pictures, any geometry that you know is appropriate. Okay, so let's start with that. So what do we know? Find the rate of change of volume. That's this. if the side length is changing at 2 inches per second. The per second clues you in that it's a per time. So I know dx dt, we'll call the side length x, is negative 2 inches per second. What else do I know? I know that that's true when the side length is 4. So I also know the side length is 4 inches. Now this might seem a little weird. The thing is that this rate is changing all the time. It's not the same. If I increase a little bit and my cube is small, I'm not going to change the volume in the same way as I might if the volume were already large. So we've got this. And the thing that we want to do, sometimes a picture is helpful. If you're going to draw a picture, then what you want to do is to label. It's important to label the picture, to label only the variables in the picture. The only values that can go on are values that do not change, ever. Is this side length changing? Yeah, that's the whole point, it's changing. So I cannot write this 4 on any picture I might want to use. I can't write that down. So you're going to label variables in the picture. You're going to label only unchanging values. And that's really important. If the value can change, you have to leave it as a changing quantity, which is a variable. Okay, so we can draw a picture here. I don't know how helpful it is. I'm not very good at drawing cubes. I don't know if that's really good. Okay, so what do we know? We know that we have a side length x, and we know we were looking at the volume. So the next thing that we want to do is now we want to write an equation that relates this variable and this variable. So look at your rates that you're interested in, pick off the variable. So we want to write down, we know that the volume of a cube is x cubed. So that's the next thing we're going to do, is to write an equation that relates the variables. We haven't gotten to the rates part yet. Don't get ahead of yourself. Okay, so v equals x cubed. That relates our variables. So now that we've done that part, right, we've handled the v part of what we're trying to find, now we need to do this part, d dt. So we're going to take the derivative with respect to time, d dt, of this. So let's write that down. So our next step is d dt. And the reason for writing it this way is to say that we are going to take the derivative with respect to time of both sides. And so we can write them out separately if we want to. The important part that I just erased is that the variables don't match, right? So we need to be careful about how we take our derivatives. So let's look over here. I'm going to write them out separately. d dt of v is equal to d dt x cubed. d dt of v is just dv dt. There's nothing else to do with that. So dv dt. And sometimes in related rates you'll have that. Sometimes you won't. So sometimes it won't work out as simple as this. Over here, variables don't match. So that means I handle the outside, 3x squared, times derivative of x with respect to time. Okay, so now what do I know? I have written an equation that relates the variables, and now I have written an equation, to say find, the equation that relates the rates. And we do that through the derivative, using implicit. Okay, so now once we've gotten to that point, now what do we do? Well, now we're ready to plug in everything we know. So do we have enough information? We're trying to find this. Awesome. Do we know dx dt? Yes. Do we know x? Yes. So we can actually just simply plug in at this point. So let's do that. So we're going to have 3 times x squared times dx dt. So 16 times 6, 96, negative 96. Negative 96 what's? Remember, it's a word problem, so it has to have a word answer. So 96, we get inches squared, another inch, so we've got inch cubed per time, per second. So this tells us that when our box is big enough that x is 4 inches on the side, and we're reducing it, the side, at 2 inches per second, so I guess that's really, really fast, how fast is the volume changing? The volume is changing at negative 96 inches cubed per second. Okay? So let's write out that last step. So here, the step was to substitute all of known values. And there will be times where it will get a little bit more complicated, and you might be missing a value that you don't know. There may be one here that you need to put in you don't know. This equation from number 4, that equation from step number 4 is what will help you find that extra value. And then the last step is to simply write the answer, and you don't need to number the steps, to answer the question. And it's important when you answer the question to use units. How do you know what the units are? dV dt. What are the units of volume? Divided by the units of time. So inch cubed per second. Okay, so take a stab at it. The one that you have to start with in homework will not have this part here. All it's going to be is this part here. This is the type, this is the information you're going to be given. You're not going to need a picture, you're not going to have any context. It's just going to say, I know I'm looking at this rate, I want to know, oh, that rate, and then I know it's going to give you an equation. So it's going to give you step 4. And so this is kind of devoid of any context or picture or geometry or geometric equations. All you need to do here is know that this is what's relating your 2 rates. So you kind of get to distill some of this down to begin. Okay, that's it.